Check one. Check one. Right. Good evening, everybody. Almost night. Good night, Yannan. Good evening, everybody. Before we start the class, confirm me whether you can hear me properly and see the video clearly. But I love you all to unmute. Can you hear?
Yes, sir. Yes,
Yes,
sir.
sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Can hear,
Or
sir.
YouTube side. YouTube side. Hari, Neil. All clear. All clear. Hurry, without any further delays, night class no. To start the section. Last week we were doing hydrostatic pressure. Done hydrostatic pressure, H rho G done, questions done, this part done, characteristics done, characteristics of hydrostatic pressure, transmission of pressure through liquids done. Can remember hydraulic jack, hydraulic press, brake system, pressure due to gases, or compressed gas part done. Gas balloon comes on to the other side. This part done. Yes, I know. We'll revise and go. We'll just come through the things and go. Atmospheric pressure, we started. Atmospheric pressure decreases when you go to high altitude, when you go levels. Atmospheric pressure decreases, that part we learned. Because of the weight of the air above that point decreases. Mercury barometer we learned. Mercury barometer we learned. Can remember how to work using a mercury barometer. Here the pressure is atmospheric pressure. Here the pressure is to mercury column. So atmospheric pressure is equal to pressure due to mercury column. Pressure due to mercury column is H rho G. H is how much? How much of centimeters you will get at what you call mean sea level?
76 centimeters.
76 centimeters. You'll get 76 centimeter at mean sea level. Density is given, G is given. You apply H rho G. What's the value we got? Can remember? This part last week done. Px equal Py. Px equal Py. Px is due to atmospheric pressure. Py is H rho G pressure. PATM is equal to 76 centimeters converted into meters multiplied by 100 multiplied by 13,600 kilogram per cubic meter. Anisa, what is this? What is this, Nevila? This is the density of mercury. Gravitational acceleration is 10. Where? Gravitational acceleration is 10 ms to the power minus 2. You do the math here. When you do the math there, you get atmospheric pressure. Atmospheric pressure is 1.036 dalamai.
0336.
0336. Yeah, you do the math. 0336.
3360.
0336 into 10
Zero.
to the power how much? 5 Pascal. We round it off, need. When you round it off, how much you will get? 1 into 10 to the power 5 Pascal. Up to there, we did last class. Finding atmospheric pressure. Did you all do the homework? Homework questions? I gave 3 homework questions. Can remember, you can't remember. Finish. On those who are done, tell what's the answer for the first one. Those who are shy, tell me, send me in the text chat box. What's the answer for the first one? Hurry, I know you are shy. Send me to the chat box, will you? What's the answer? Homework, eh? Send me in meters. They're asking the, what? If water is used instead of mercury, what will be the vertical height? Send me in meters. Where? Oh, no, some fellows are doing it now. Yes, I'm talking to you. Hurry. Different answers are coming. Is my voice down? Eh? No. Ikni. Those are wondering, was there a homework? What's the question asking? If water is used instead of mercury. They were using mercury, no? Now water is, this is water. If water is used instead of mercury in a barometer, what will be the vertical height? They are asking
10 meters.
what will be the vertical height? Don't tell me 76 centimeters. 76 centimeters is for mercury. What will be the vertical height of water at mean sea level? Now, H you need to find. Density of water is given. Rho is given 1000 kilogram per cubic meter. Gravitational acceleration is given 10 ms to the power minus 2. H they are asking. Apply the equation H rho G. To apply the equation H rho G, equation is hydrostatic pressure is equal to H rho G. Rho is there, G is there. Rho is there, G is there. They are asking H. To find H, one more thing you need. What's that? What's that?
Hydrostatic pressure.
Hydrostatic pressure.
Hydrostatic pressure. Can you pressure you need? You need the pressure here. You need the pressure here. That is hydrostatic pressure. This pressure is equal to this pressure. Y'all tell me what is the pressure there?
1 into 10 to the power 5 pascals.
And hurry. At mean level, we already calculated. What is the atmospheric pressure? 1.0336 into 10 to the power 5 Pascal. Don't go to use this. Even if you are done this, doesn't matter. Easy is use the round off value. 1 into 10 to the power 5 Pascal. So, pressure at mean sea level, we already know. What is the pressure at mean sea level? 1 into 10 to the power 5 Pascal. And he say it is not given in the question, no need to give it. You should know. You should know pressure at mean sea level is 1 into 10 to the power 5 Pascal. That is the pressure here. That one they won't give. They didn't give in the question. They didn't give in the question. Hydrostatic pressure there. They have not given it. So pressure you should know. Previously we did it. 1 into 10 to the power 5 Pascal. Density of water is given 1000 kilogram per cubic meter. Gravitational acceleration given 10 ms to the power minus 2. H they are asking. Remember, if there is a equation with 4 variables, guaranteed 3 variables you should know. Then only you can find one variable. That is how math works. If there is a equation with 3 variables, 2 you should know, then 1 you can find. If there is a equation with 4 variables, 3 you should know, then 1 you can find. So to apply HP equal H rho G, you should know 3 things. HP you should know, rho you should know, G you should know. Rho and G are given in the question. HP not given. You should know that atmospheric pressure is 1 into 10 to the power 5 Pascal. From there you can find. Now the question is nothing. Those who did it using 1.0336, don't panic. Even your answer is correct. Your answer is more accurately correct. But you can apply directly. Round of value you can get. Will apply. Already the pressure is there. 1 into 10 to the power 5 Pascal. H you don't know. What you don't know, keep it as H. Density you know. 1000 kilogram per cubic meter. Gravitational acceleration you know. 10 ms to the power minus 2. If you need to find H, you need to subject H. If you subject H, all the other things go to the other side. Multiplication on other side become division. Then H is equal to 1 into 10 to the power 5 Pascal divided by 1000 kilogram per cubic meter multiplied by 10 ms to the power minus 2. Now, some fellows get panicked when they see equations like this. Slowly do it. I'll remove all the units, then equation will be easier. I can write 10 to the power 5. Write it as 10 to the power 5 divided by 1000 into 10, 10,000. H will come in meters. I'll take this one more step ahead. This 10 to the power 5 divided by 10,000 is 10 to the power 4. I'll take this one more step ahead. 10 to the power 5 divided by 10 to the power 4. What will happen? 10 to the power 4 will fully cancel off. 10 to the power 5 will cancel off. Remaining 10 meters. So the height is 10 meters. Those who took 1.0336, you will get 10.336 meters. Those who took 1.0336, 10.336 meters, you will get. Round it off to 10. So if you use water instead of mercury, what will be the mercury? What will be the height of the water? 10 meters. Wait, I'll give time to write. First tell me, then is this kind of a barometer practically possible to handle?
No.
No, sir.
No, sir.
No, sir.
No, it's not easy to handle.
No.
No, sir.
Right, 10 meters kiyanne such a big height. Now your house is usually about 8 meters. The house roof comes 8 meters. A little bit more than that. Such a big this thing. Maybe in one place you can fix and keep, but you can't measure the pressure using those things. Even mercury barometer is somewhat big. You need at least 1 meter long tube. By 76 centimeter height, you should give that space. At least 1 meter long tube you need to use. Water, it's way more higher than that, 10 meters. Okay. Those who got any other answers, check your calculations. Some fellows don't know now. Multiplication or division. Those things properly check. Others, those who didn't do, quickly write it. How did 10,000 come? 1,000 into 10, how much? 1,000 into 10, how much? 10,000. Okay. Not over. Second question. So I know not using the units is easy, but with the units, can you do the calculation? Yeah, sure. Just for fun, we'll do with the units. With the units, this part you should write units and this part you can't ignore. With unit substitution is needed. After that, whatever the mathematical Gilmart method you want, you can use. In final answer should come. This part is this part is important. This part important. You should properly show how the units come. We'll play a little bit with the units. Now from here only I ignore the units and when will not ignore the units will work out. 1 into 10 to the power 5 Pascal divided by 1000 kilogram per cubic meter 10 ms to the power minus 2, right? H is equal to 1 into 10 to the power 5 Pascal divided by 1000 kilogram per cubic meter multiplied by 10 ms to the power minus 2. These are not necessary. As person has asked to do with the units, I'll play a little bit with the units. H is equal to 1 into 10 to the power 5 Pascal. Tell me Pascals in basic unit, fundamental unit. Pressure, what's the fundamental
kgm
unit?
minus kgm to the power minus 1 s to the
kgm to
power
the power
minus
minus
3
1, s to the
s
power
to the
minus
3
minus
2.
2.
to r2.
So pressure, Pascal, I wrote it in fundamental unit, divided by 1000 kilogram per cubic meter multiplied by 10 ms to the power minus 2. H is kg cancel off. M to the power minus 3, m to the power minus 1. Solve this. These two cancel off, m to the power minus 2. Neither. These two cancel off, m to the power minus 1 in the denominator. M to the power minus 1, take it on top. M to the power plus 1. No need to write plus 1 m. So all the m's will cancel off. S to the power minus 2, s to the power minus 2 cancel off. To get the final answer in m, 10 meters. The person who has to do with the units, clear? Okay. Second question. Second question. A mercury barometer. Now water story is over. Mercury barometer gave a height of 20 centimeters of mercury column on top of a mountain, of top of Mount Everest. Calculate the atmospheric pressure on top of Mount Everest. Density of mercury is there, gravitational acceleration is there. Height is 20 centimeters. There you go. Question 2. Height is 20 centimeters. Can we do the question using centimeters?
Can't, sir.
Can't. To convert to meters, 20 over 100 meters. Centimeter to meter, you divide by 100. Density of mercury is given 13,600 kilogram per cubic meter. Gravitational acceleration to the power minus 2. They are asking the pressure up of Mount Everest. Apply the equation. We can't directly find atmospheric pressure. Atmospheric pressure is equal to the hydrostatic pressure there. Hydrostatic pressure is H rho G. H is there 20 over 100 meters multiplied by. Density of mercury is there 13,600 kilogram per cubic meter. Gravitational acceleration 10 ms to the power minus 2. Do the math there. From that, you can find the atmospheric pressure at top of Mount Everest. So if I do it, 0000 cancel off. 136 into 2, that is 272.
00.
1, 2. 2 zeros you put. 27,200 Pascal. Tell me that in kilopascal. You can leave the answer like this, but tell me that in kilopascal.
27.2 kilopascal.
And you divide by 1000. 27.2 kilopascal. Big values always try to keep it in kilopascal. But however, this one also okay. This one also okay. Quickly write it. Those who have went wrong, I'm pretty much sure your errors are because of the mathematical calculation, not because of the science there. Okay. Question 3. Send me the answer. Question 3. Send me the answers. Right. Will work. A mercury barometer showed a height of 90 centimeters at a bunker. Bunker is underground. Calculate the pressure in the bunker, density of mercury given, gravitational acceleration given. Height is 90 centimeters. Question 3. Height is 90 centimeters. That in meters, 90 over 100 meters. That in meters, 90 over 100 meters. Density, by now, density of mercury would have been recorded in your mind. 13,600 kilogram per cubic meter. Gravitational acceleration 10 ms to the power minus 2. Apply the equation. Atmospheric pressure is equal to the hydrostatic pressure there. Hydrostatic pressure is equal to H rho G. H is 90 over 100 meters. Density 13,600 kilogram per cubic meter. Gravitational acceleration 10 ms to the power minus 2. From there, you can find the atmospheric pressure. Do the math. 00, 1, 2, 0 cancel off. 9 into 136. 10 into 136 is 10 into 136 is 1360. Minus 136 is 4, 2, 2, 1. Now dealing with zeros, 1, 2 zeros remain. 122,400 Pascal. That in kilopascal if I write.
22.4 kilopascal.
122.4 kilopascal. Any answer correct? Interesting questions, and don't think this is a headache. Headache questions are there. This is not a headache question at all. Don't think these are headache. These are questions where you can surely score in your exam. If you get these types of questions in the exam, be happy. First of all. How did you do the maths easily? Maths part is oh, 9 into 136. No, I did 10 into 136 minus 136. 10 into 136 minus 136 is 9 into 136. 10 times, then I minus 2, minus 1. That way I went. Hurry, maths part is however there. That you can't ignore. Maths will everywhere. Maths will come. What we learn from this? I can't understand the maths part, but science is easy. That you need to develop. Do more and more questions. Then automatically your mind will get developed into thinking different ways of solving the same question. Right? So you got sore throat. Sore throat Navi today from morning work. From morning to continuously until 4 o'clock. 4 o'clock we had some until afternoon we had lectures. After that we had some program rehearsals in the university. Finished it, came 4:30 class. Today got late to start. 5 o'clock only I started the grade 11 class. After the grade 11 class, 7:30 it finishes. 7 o'clock it finishes. 7 to 8:30 again grade 9 class. After that your class. So are you still studying? I think, what do you think about me? I'm not that much old, right? Hurry. Back to work. Now see what we learned from this. What we learned, Lamai? We learned something. See, pressure is 27,000 Pascal. Him will tell. Pressure is 27,000 Pascal. Pressure 27,000 Pascal. Height is 20 centimeter. 27,000 Pascal pressure, 20 centimeter. 1 lakh pressure, 90 centimeter. 20,000 Pascal, 20 centimeter. 1 lakh pressure, more than 1 lakh, I'm just rounding off. 1 lakh pressure, 90 centimeter. That means, what can you tell about the height of the mercury column when the pressure increase? What can you tell about the height of the mercury column when the pressure increase? 27,000, 20 centimeter, 1 lakh, 90 centimeter. What can you tell about height of the mercury column when the pressure increase?
Height decreases.
Both are directly
Height.
proportional to each other.
When pressure increases, height also increase. Pressure 27,000, height 20 centimeter. Pressure more than 1 lakh, height 90 centimeter. When the pressure increase, height of the mercury column also increase. Now think opposite. When pressure decrease, height of mercury column also
Decrease.
Decrease.
height of mercury column also decrease. It also decrease. Question 3. Question 3 anyway. Important part. What's the important part telling us? When atmospheric pressure increase, vertical height of mercury column will also increase. When atmospheric pressure decrease, vertical height of mercury column will also what? Decrease. Please underline or highlight this full sentence and key. Okay. Right. Finally going to Aneroid barometer. Finally going to Aneroid barometer. Aneroid barometer. Right. We already learned there are two types of barometers. Mercury barometer, aneroid barometer. Now, mercury barometer. You all tell me, what's the main disadvantage in mercury barometer? Just practice.
So difficult to maintain.
What's the
Liquid.
main disadvantage in mercury barometer?
Difficult to maintain.
It is
Difficult.
quite expensive.
Yeah, answers are coming. One, our maintenance you can't actually move it easily. Neither.
Yes, sir.
It is there. It's a bit difficult to move. Our mobility is less. Let's take you are going on a flight. You are a pilot now. You are flying an aeroplane now. Sorry. A pilot is there in the cockpit there. He wanted to measure the pressure. Onnapute, can he keep a mercury barometer there in the cockpit? That 1 meter long. He takes some turns. What will happen to the mercury? Mercury will spill. Mercury is toxic as well. Mercury is toxic as well. So is it a mobility part? It's a bit hard, neither. It's way more hard to move it. Mobile part is hard. That is where aneroid barometer comes into play. Aneroid barometer, a liquid scene, those things are not there. Liquid, nothing like liquid. What is there? There is a metal cavity. A cavity made of metal sheet. A cavity made of metal sheet. Sorry. This one is connected. We'll do a connection. There's a connection like that. Sorry. From there, you have a meter. That's the meter. Is a scale. That has an indicator. That has an indicator. That indicator is connected to this metal cavity. That indicator is connected to the metal cavity. Now practically think. Let's take outside pressure is increasing. Now what did I tell? What is pressure? When I tell pressure, what should come into your mind? or squeezing feeling. When outside pressure increases, this metal cavity gets squeezed. This metal cavity gets squeezed. When the metal cavity gets squeezed, this part will be pulled down. Practically think, when the metal cavity gets squeezed, this part will be pulled down. When that part is pulled down, this part is also pulled. When that part is pulled, indicator will move. Mechanically think, when the outside pressure increases, cavity get pushed. When the cavity get pushed, this part moves down. When that part moves down, this get pulled. When that get pulled, indicator will move. Depending on how much the indicator is moving, we can directly measure the pressure. No need to do any calculation. Depending on how much the indicator is moving, you can directly measure the. That's an aneroid barometer. Just you see, the number will be there. Okay. Now, pilot can't take a paper and a pencil and start measuring the length there, do the multiplication there, find this thing using a mercury barometer. So this one directly shows you the pressure. Now, actually, more than this, direct digital barometers are there. These are very old things, old syllabus things, very old things. Now we don't use these things. Aneroid barometer. There are barometers that do not contain a liquid. They are known as aneroid barometer. They don't have a liquid. It has a cavity bounded by thin metallic wall in which air has been executed. When the pressure outside barometer varies, the shape of the wall of the cavity also varies. An indicator attached to the cavity wall rotates with the variation of the shape of the wall. The pressure can be read out from the attached. So this is the cavity. When the cavity moves, this moves. Depending on that, you can read the pressure. That's how an aneroid barometer works. That's about measuring atmospheric pressure. Got it? Okay. Now, what are the applications of atmospheric pressure? Applications of atmospheric pressure. Applications of atmospheric pressure. Application number 1. When you are drinking water using a straw, think about that. You drink water. Using straw. There you go. You have the beautiful cup. Inside that water is there. You put a straw there. Straw is there. You are trying to drink some water using the straw there. You are trying to drink some water using the straw there. When you are drinking water using a straw, what you do? You put the straw inside water and you suck the air in the straw. You suck the air in the straw. The moment you suck the air in the straw, all the air in the straw goes inside your mouth. When all the air inside the straw goes inside the mouth, pressure inside the straw will decrease. When you suck the air, all the air goes inside the mouth, pressure inside the straw decreases. So now pressure in the straw is very less. Now coming outside the straw, this point. This point has a very high pressure. Why? There is a height in the liquid there. Due to that height, there will be H rho G pressure. There is a height. Due to that, there will be H rho G pressure. Above that, you have the atmosphere. Atmosphere is also pushing the liquid. Atmospheric pressure is there. So atmospheric pressure is there. H rho G pressure is there. Therefore, pressure here is very high. Pressure there less. Pressure here high. I take this point as B. I take this point as A. Pressure at A is high. Pressure at B is low. Correct? No? When you suck the air, all the air goes inside. Pressure decreases. Pressure at B is less. But outside, nothing has happened. H rho G pressure is there due to the height of the water there. Above that, atmosphere is there. So atmosphere is pushing. Water is pushing. Altogether, here the pressure is high. So pressure at A is high. Pressure at B is low. When there is a difference in the pressure, what will happen? From high pressure to low pressure, liquid will flow. From high pressure to low pressure, liquid flow. Not only liquid, anything flows like that, Lamai. From high pressure to low pressure, only anything flows. Air. Air flows from high pressure to low pressure. That's how wind is created. Current. Current flows from high pressure to low pressure. That's what you call as potential difference. Any water. Water flows from high pressure to low pressure. So here high pressure, here low pressure, high pressure to low pressure, water will flow. That's how a straw. We don't think about that. No, we buy the Milo, we put that straw inside. Sometimes that straw doesn't go inside, or a paper straw. That one, however much we try, sometimes it can't. We start drinking. We never think of the science behind it. So what's the science behind? You put the straw, you suck the air, decrease the pressure. Inside pressure is high. Have you all tried this? Tell me those who have tried this. Milo packet is there. You put the straw, you suck the air, the milk there comes out. Have you all pressed the Milo packet while drinking? Or have you all squeezed the Milo packet? When you squeeze the Milo packet, what can you tell about the speed of Milo coming out? Increase the, decrease the speed of Milo coming out? Increase. Aye. Now I have told you, squeezing is applying pressure. The more pressure you apply at the bottom, more faster the water, whatever it is, will come out. So basically, there the flow is due to pressure. Have you done so? Of course, yes. Natu? Right. When you drink Milo, first you put the straw, you drink like a normal human being. After that, a crick crick sound will come. At that time, you press it and somehow take all the Milo. After everything is finished, you blow it, you jump and you blast it. That's how you finish off a Milo pack. Right? Don't do it in the school. Principal will come and he will blast you. Huh. Hurry. Drinking with the use of a straw. When we drink using a straw, we suck the air inside the straw and that air enters the mouth, reducing the pressure inside the straw. The pressure at the liquid surface outside the straw is at the atmospheric pressure, while the pressure inside the straw is less than the atmospheric pressure. Therefore, the atmospheric pressure pushes the liquid in the glass into the tube and the liquid moves through the straw. From atmosphere, it gets pushed. H rho G pressure, together with that, it goes. That's the theory behind it. Sorry. Next. Second application. What we are learning? We are learning applications of atmospheric pressure. Second application. Removing water using using siphon method. Anis, what is siphon method? Listen, Nelly. What is this siphon method? Tank. Fish tank. This is a fish tank. Sorry. Fish is also there. I am not going to draw the fish. Fish tank is there. Now you are going to clean the fish tank. Right. Now let's say fish tank is very big. Now, when you are cleaning the fish tank, what you do? You first remove the water inside that. Right? You have to remove the water. If the fish tank is very big, before that, we have to remove the fish there. That's some powerful. We transfer the fish into some other place. Right? First, you transfer the fish. That's some powerful. You transfer the fish into some other bucket or something. After that, now let's take fish tank is very big. You can't lift the fish. You can't lift the fish tank, right? You can't lift the fish tank. Now fish tank is there. Now how are you going to remove the water? How are you going to remove the water? Sir, take a small cup, put it inside, take the water, put it out. Hurry. That is one method. Normal method. Now you are a science student. Using science, how are you going to remove the water? Sir, connect a pump there. Pump is not there. Another method is there. You call it siphon method. What is that method? Now fish tank is there. Fish is not there. Take the fish away. Next, what you do? You take a bucket. You keep the bucket nearby fish tank. Near the fish tank, you keep the bucket. Don't take the wash bucket tank. You will get hit from your mother. Don't take that separate bucket tank. Keep the bucket nearby. Now you take a flexible tube. Sorry. Flexible tube means to the fish tank itself, we put oxygen. Oxygen, that motor is fixed with a tube, something like that. Such a flexible tube. You take the tube, right? Now tube is there. You show the tube to the tap, fill the tube with water. First you fill the tube with water. Now let's take this the tube. You fill the tube with water. Now you show it to the tap and hurry, get filled, hurry. Fill it with water. Now you close it from both the ends like this. Even if you close it from one end, doesn't matter. Water doesn't come out. If you want, you try it and see. You close it from one end, water doesn't come out. But it's okay to close it from both the ends. Now you close it. Even one end doesn't matter, right? Water doesn't come out. If you want, you try it and see. You close it fully from this side, water doesn't come out. When you release it, water will come out. When you close it, water doesn't come out. Water, you close it. Right? One tube. Now inside this water is there. Right? One tube, you put it inside the fish tank. Listen, now don't type these things, messages. One tube, you put it inside. The other tube is near the bucket. Now you remove it. Remove the fingers. Open it. Remove the fingers and open it. So if I draw and show, tube is there. You close it one, even if you close only one end, that doesn't matter. You put it. After you put it inside, now this one should be inside the fish tank. Now you open this. Automatically the water comes out. Automatically it happens from this side. Water comes out. You don't need to do anything. You just have to hold it until all the water goes. How? How? I have seen this in TikTok. You hurry. TikTok videos are there. How? Hurry. How kila man kiyanna? Now see, I'll take this point as point A. This point as point B. What is there near point A? What is there? A kyanne H rho G pressure is there. above that atmospheric pressure is also there. So if you take the pressure at A, atmospheric pressure is there, H rho g pressure is there. Point A, atmosphere is pushing it, H rho g is pushing it. Look at point B. Point B is directly exposed to the atmosphere. That means only atmospheric pressure is there. Here, atmospheric pressure, H rho g pressure. Here, directly atmospheric pressure. Point A, point. Now, your turn. You all tell me, A and B, where you have high pressure.
A.
All tell.
A, B,
You have high pressure. Why? Atmosphere plus H rho g. Pressure at A is high. Pressure at B is low. When there is a pressure difference, what will happen? From high pressure to low pressure, what will flow? Water will flow. That's the reason. Right? But to start it, initially you have to fill it with water and keep. To trigger the initial flow, you have to fill it with water. That's why we fill it with water and put it inside. Otherwise, our initial flow won't go. Our initial triggering won't happen. So for initial triggering only, you fill it with water and put it. That is what our syllabus tells. Another method is there. What is that? Don't go to fill it with water or anything. Just bucket is there, just fish tank is there. Don't go to fill it. Take the tube, put the tube inside this.
With
The
mouth.
other part, keep it in your mouth. Suck it. Suck the air. When you suck the air, you will see that the water is coming. When the water comes very close, remove it from the mouth. Don't hold it until the water comes into the mouth. When the water comes near the mouth, you remove the mouth and then put it inside. Timing should be properly coordinated. You suck the water. When the water comes nearby, you remove, you put it inside. Don't use this for fish tank. You use it for what?
Petrol.
And
Petrol extracting.
people take petrol from petrol tank. This is how they do it. Put a tube, suck the air. The petrol will be coming. When the petrol comes closer, you remove this thing and then it comes out. That's how people take petrol from the petrol tank. And sometimes petrol goes inside. Then you wash the mouth. Removing water in a tank using siphon method. Figure illustrate the use of siphon method to draw the water from the tank A situated at higher level to tank B situated at lower level. Initially, the tube has to be filled with water and one end, you can press one end, pressed with a finger so that water does not flow out, and then the tube should be lowered down to A. Thereafter, when the finger is removed, water starts flowing from tank B to tank A. Water starts flowing to tank B from tank A. The pressure at the end of the tube in A is equal to the sum of the pressure due to water column in A above the end of the tube and atmospheric pressure. So here is H rho g pressure and atmospheric pressure. Till the end of the tube B is exposed to the atmosphere, the pressure there is equal to the atmospheric pressure. Therefore, the higher pressure in the tank A pushes the water to the other end of the tube at the tank B, which has a lower pressure. Finally, action of a rubber sucker. Action of a rubber sucker. These are things that you have seen in the life, but now you are learning more scientifically. Sorry? Rubber sucker. What is this rubber sucker means? There's something like this, like what? Like this. Let's say you have a glass. මෙහෙම that's made of rubber. When you press it to the glass, it get attached. Here you can hang something. Have seen rubber suckers like?
Yes, sir.
Right.
Yes, sir.
How do you use?
Yes, sir.
You press it to a glass, a smooth surface. It get attached. Then you can hang
Yes.
something here. Now this is the side view. Front view will be something like this. That's the front view. Yeah, we used to hang something in the vehicles and all. We used to hang something. Toy guns are there. Harry, toy guns are there. How does it work now? Now listen. You keep it to a smooth surface, usually glass. Press it. When you press it, air inside will go out. Correct? When you press it, air inside will go out. Even sometimes you can hear cheek sound. When the air goes out, or cheek sound you can hear. When the air goes out, pressure inside will decrease. Correct? No, air is going out. Pressure decreases. So pressure inside decreases. But outside, if you look, outside you have atmosphere. So you have the atmospheric pressure. Here you have the atmospheric pressure. Atmospheric pressure is higher than the pressure inside. Atmospheric pressure is higher than the pressure inside. Why? Inside all there you have sent out. The pressure inside decreases. Outside you have a lot of pressure. Atmospheric pressure is there. So atmospheric pressure is greater than inside pressure. As atmospheric pressure is high, what will it do? It will squeeze, it will press the rubber sucker towards the wall. Outside pressure is high, it will press, it will squeeze the rubber sucker towards the wall or glass, whatever you have. Right? But in case if air comes in, then what will happen?
Fall down.
It will remove.
Inside and outside pressure will become equal. Inside also air comes in, inside also atmospheric
It
pressure
will remove.
will become equal. If it become equal, can this press? No,
Can't.
it will fall down. That is why if you want to remove this, what you do? Using your nail, you just remove a small part. You put the this thing and you remove a small part. What will happen? Automatically it gets removed. You hold it from here and try to remove that. It never comes. You hold it, you put your finger here, the nail there, remove it a little bit, air goes inside, it comes out. You all tell me, in case if the surface has any dust, will it get attached?
No.
No.
Why? If there is dust, air can't go out.
Yeah, sir.
Even if air goes out, some air can come out. There is a way for the air to come out, come in. So when air comes in, this won't. But there is no any glue there. It works on pressure. Action of the rubber sucker. When a rubber sucker is pressed onto a glass surface, most of the air between the two surfaces is removed, leaving only a little air between the sucker and the glass surface. Then, since the pressure inside the rubber sucker is less than the atmospheric pressure outside, the sucker is held pressed to the surface by atmospheric pressure. The rubber sucker would function properly only if there is no airflow between the edge of the sucker and the glass surface. Ta-da! Applications of atmospheric pressure is done. Last section, final section. Or any other YouTube people? The cavadu. No, not yet. Last section. Listen, now this is the most important part. Now the most important part, listen very carefully. Right? Ask from your grade 11s, your friends in grade 11, your IL Akka in grade 11, upthrust part, Archimedes principle, what the important section. Listen very carefully. Hurry. Flotation. Flotation. Under flotation, we learn about upthrust. First, we learn about upthrust. Listen very, very carefully. Under flotation, first we learn about upthrust. What is this upthrust? First, I'll tell the definition, then I will explain. The upward force acting on an object when the object is partially or fully immersed in a fluid is upthrust. What is upthrust? Upward force acting on a object when the object is partially or fully immersed in a fluid. Hurry. Let's take, you have some water. You put something inside the water. Now this object is fully immersed inside this water. Fully immersed, is fully inside, fully immersed. When the object is fully immersed, there will be a upward force acting. That upward force is called. Not only when it is fully immersed, not only when it is fully immersed. Now see, Lamai, see, object is partially immersed. It's not fully immersed, partially immersed. Even if the object is partially immersed, there will be a upward force acting. Again, what is that? Then what is upthrust? Upward force acting on an object that is partially or fully immersed in a fluid is upthrust. Nothing big. You go to a swimming pool, you jump into a swimming pool. Won't you feel an upward force? Huh? Won't you feel upward force? That is upthrust. Upthrust. Upthrust is a type of force. Tell me, Lamai, what's the unit of upthrust? If it is a type of force, what's the unit of upthrust?
Newtons.
Uh,
Newton. Should be Newton. Why? If it is a type of force unit is Newton. Upthrust is upward force acting on an object immersed in a fluid. Here the object, upward force is upward. Downward, however, weight is there. Downward, however, weight is there. Right. Now listen. Now listen. Right. There you go. There you go. You have an object. I hang it in a Newton spring balance. I hang it using a Newton spring balance. Newton spring balance. Using Newton's balance, I can measure the weight. It will have a certain weight. it will have a certain weight. That weight is called real weight. What is that weight called as? Real weight. Really, that's the weight there. Hang it. The weight there is real weight. Now, for example, this phone, if I hang it using a Newton balance, if I measure the weight, that is a real weight. This water bottle, I hang it using Newton spring balance, I measure the weight, that's a real weight. All right. So that's a real weight. Now what I'm going to do, I immerse this setup. Inside a fluid. When I immerse it inside a fluid, now the weight won't be same as the previous one. We feel something like weight is less. We feel something like now the object's weight is less there. So the weight we are feeling now is called apparent weight. The weight we are feeling now is called apparent. I'll name it as WA. When the object is outside real weight, when the object is inside a fluid, the weight will be a little bit less. That is apparent weight. Why? Why we feel that the weight is less now? What's the reason? The reason is this. Real weight is acting down. Yes. But you all tell me, when the object is immersed in a fluid, additionally there is upward force. What is that upward force?
Upthrust.
When there is an upward force, tell me, what will happen to the overall downward force? Will increase or decrease?
It will reduce.
Decrease.
It will decrease.
That's why we feel as if the weight is less. Is it real weight? No, that's not the real weight. You name it as apparent weight. The moment you take it out of the fluid, you will again feel the real weight. So when the object is immersed inside, we feel a apparent weight. So if I take the reading here, real weight reading, apparent weight reading, what can you tell about? Reading 1 and reading 2. Which one is greater?
Reading one.
One is greater than
One.
2.
Why? W is greater. R2 will be less. Why? WA is less. So outside, real weight. Inside a fluid, apparent weight. Okay. How can I mathematically calculate the apparent weight? How can I mathematically calculate the apparent weight? Very simple. Apparent weight is equal to real weight minus
Upthrust.
Make sense?
Um,
Apparent weight, overall downward weight is equal to the real weight, the big weight, minus the upward force, upthrust. Downward big weight, upward upthrust, you subtract it, you get the final weight in the fluid. So apparent weight is equal to real weight minus upthrust. Apparent weight is real weight minus upthrust. Now, for example, just practical thing can tell me, let's take an object, real weight is 100 Newton. When I put it in a liquid, upthrust is 20 Newton. Now tell me, Lamai, what's the apparent weight?
80 Newton.
80 newtons. 80 newtons.
Really, it has 100 Newton. Now you have an upward force. When upward force is there 20 Newton, the final downward force will be 80 Newton. Let's take, I hang it using a Newton spring balance. Reading R1 is 100 Newton. Now tell me, what's the reading R2?
80 Newton.
80 Newton. Now the reading will be 80 Newton. Real weight is 100 Newton. Now the weight will be 80 Newton. So previously it's 100 Newton now. Now the reading will be 80 Newton. Very practical thing. Practical thing, when you go inside a swimming pool, Won't you feel like your weight is less? Hmm? Let's say you and your friend, both of you go under the swimming pool. You are trying to lift your friend under the swimming pool. Hmm? Inside the swimming pool, you are trying to lift your friend. And later, outside the swimming pool, you are trying to lift your friend. When it is easy to lift the friend? Inside the swimming pool, the outside the swimming pool?
Inside.
Inside the
Outside.
swimming pool. Inside.
Inside the
Inside.
Outside.
Inside you go, inside the swimming pool, you can easily lift your friend. Even with one hand, you can lift the fellow. Outside swimming pool, however much you try, that fellow doesn't come up. You know what I mean? That's the reason. Huh. The weight of an object is actually called real weight. When an object is immersed in the fluid, due to upthrust, there will be an apparent weight acting which is less than the real weight. So under that a box is given. We'll write this. Apparent weight equal real weight minus upthrust. Right that?
Finish it. Yes.
Okay, no? Example is given. Hang a weight of 100 Newton on Newton balance. Reading on the Newton balance will be how much? 100 Newton. Immerse the weight inside water. Let the upthrust be 20. If the upthrust is 20, what will be the new reading?
80.
80 Newton. The new reading will be 80 Newton. Real weight is 100. Now the apparent weight is 80. Another box is given. There will do the calculation and show. Apparent weight is equal to real weight minus upthrust. Apparent weight is equal to real weight 100 Newton minus 20 Newton. What's the apparent weight? 80 Newton. Write it and keep. Hurry. Under that a small question is given. Try. Try the question. Tell me the answer. Okay. Question. Mass of an object is 25 kg. Calculate the real weight. My mass of the object is 25 kg. Mass of the object is 25 kg. They are asking the real weight. Roman 1. They are asking the real weight. How to calculate real weight? Multiply the mass by gravitational acceleration.
250 newtons.
Mass is 25 kg. Gravitational acceleration 10 ms to the power minus 2. What's the real weight?
250 newton.
Yeah, real weight 250 Newton. Real weight 250 Newton. Roman 2. When the object is immersed in a fluid, the upthrust acting is U. Derive a relationship for WA, apparent weight, in terms of U, WA, W. Now we all know. Tell me. WA is equal to
W minus
W minus upthrust. Roman 3.
upthrust.
If WA is 150 Newton, calculate the upthrust. WA is given. WA is 150 Newton. It's real weight already. We know no 250 Newton. They are asking upthrust. How much?
100 newton.
Take this to the other side. Take this to the other side. Minus U become plus U. 250 Newton plus 150 may become minus 150. So upthrust is 100. Got this? Yes? No?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. Hurry. Last part. Onnapudi. Now the important thing starting. Archimedes principle. Archimedes principle. Listen, important section. Archimedes principle. Before going to Archimedes principle, I will teach you all a small activity. With that activity, we can learn Archimedes principle. Now, this is not Archimedes principle. This is a small activity. Activity. What's the activity? You take Eureka vessel. What vessel? Eureka vessel. Open the mouth and tell what vessel? Eureka vessel.
vessel.
What is this? Eureka vessel means I will draw and show. This is Eureka vessel. You can fill up to the brim. If you try to fill any more, it will overflow. That's a Eureka vessel. Near the Eureka vessel, you keep another container. You fill the Eureka vessel until the brim. Until here you fill. I say what? You fill it with what? Now what? Now you take a small object. Slowly immerse it inside. You immerse the object slowly inside. There you go. Listen, you slowly immerse the object inside. When you immerse the object inside, practically think and tell what will happen to the water.
It
Water
will
will
go
come.
into the container.
Water comes out.
The Eureka jar.
Now the magic. If you measure the volume of the object immersed in the fluid. I repeat the sentence. If you measure the volume of the object immersed in the fluid. Volume of the object immersed in the fluid means This is the volume of the object immersed in the fluid. That part is only immersed in the fluid. Then that is the volume of the object immersed in the fluid. Let's take that as 100 milliliter. This part is immersed in the fluid. Volume of the object in the fluid is 100 milliliter. And if you measure the volume of the water that has come out, that is also what?
100 millimeters.
100 millimeter.
Or seen,
Milliliters.
100 milliliter. 100 milliliter. That is also 100 milliliter. Now let's say I immerse the object furthermore inside. Let's take volume of the object immersed in the fluid now is 150 milliliter. Water will come out. What will be the volume of the water?
150
150,
milliliters.
Milliliter.
150 milliliter.
Slowly put the things to the mind. We're going to build a connection now. Don't lose the focus. Let's say you immerse the object fully inside. Fully now inside.
200
Let's say
milliliter.
volume of the object inside the liquid is 200 milliliter. Water will come out. When you immerse something, water will come out. What is the volume of the water?
200 milliliter.
200
200 milliliter.
to
Now see. First instance, volume of the object inside the liquid is 100 milliliter. We don't care about what is outside. What is outside didn't come to the liquid. What is inside the liquid is 100 milliliter. Volume that came out is also 100 milliliter. When you immerse it more, some more water will come out. Volume of the object inside the liquid is now 150 milliliter. Volume that came out is also 150 milliliter. Now I fully immerse it inside. Volume of the object fully inside is 200 milliliter. Then volume of the liquid that comes out is also 200 milliliter. From this, what can I tell? I can tell volume of the object immersed in the liquid. Volume of the object immersed in the liquid. And volume of the liquid that comes out. Both are
Equal.
again see, volume of the object immersed in the liquid, volume of the object immersed in the liquid, and volume of the liquid that comes out. Here 200 milliliter is inside, 100 milliliter came out. 150 milliliter is inside, 150 milliliter came out. 200 milliliter inside, the 200 milliliter comes out. Volume of the object immersed in the liquid and volume of the liquid that comes out are equal. I will tell this little bit more scientifically. Volume of the object immersed in the liquid and volume of the liquid that displays out. Displays means displays coming out. Volume of the liquid that displays out are both correct. No? You go to the bathroom. You have the bucket there. Fill it until the brim. You put your hand inside. Now let's take this is the bucket. Go. Now let's take this is the bucket, the brim of the bucket. Sorry. You put the hand inside. You put the hand inside. Make a bucket. This is a bucket. You put your hand inside. When you put your hand inside, some water will come out. When you put some more water will come out. When you put your full hand inside, more and more water will come out. When you fully get inside the bucket, all the water will come out. What can you tell about the volume of the water that has come out and volume of you inside? Both are what?
So
Equal.
equal.
Correct? Now, when you put your
Equal.
hand, a volume equal to your hand will only come out. When you put your full hand with the elbow, that full part will come out. When you fully get inside, your volume, the space that you are consuming will come out. Archimedes doesn't need to tell this. Even grade 6 child can tell. Put hand inside, volume equal to the hand comes out. Put yourself inside, volume equal to you will come out. But Archimedes told this more scientifically. How did he tell? He told volume of the object immersed in the liquid and volume of the liquid that displaces are okay. But remember, it is the volume of the object that is immersed in the liquid. We don't care about this. When your hand is inside, a volume equal to your hand will only come out. Will a volume equal to your body come out? Tell me.
Yeah.
Hmm? When your hand is inside, a volume equal to your hand will only come out. Will a volume equal to your body comes out?
No, sir.
No. So whatever that immerses inside, that volume will display out. A simple act. Now tell me, did you understand the activity?
Yes, sir.
Yes, sir.
Understood that part?
Yes, sir.
Still, I didn't teach the Archimedes principle. Just the activity I taught. Sorry. Activity. Take a Eureka vessel, fill it up to the surface with water. When you immerse an object, when you immerse an object, volume of the object immersed is equal to the volume of the displaced fluid. Underline or highlight. Volume of the object immersed is equal to volume of the displaced fluid. Underline or highlight. That is an activity. From this, we can learn Archimedes principle. From that, we can learn Archimedes principle. Right. Now coming to the principle. What is Archimedes principle telling us? What is Archimedes principle telling us? Very simple. There you go. You have a Eureka vessel. You fill it. Now listen, now don't lose the focus. You fill it until the brim. You keep a container nearby. You immerse an object inside. You immerse an object inside. Slowly you are immersing it. Slowly immersing. Now it is partially immersed. Now it is fully immersed. Partially immersed. Fully immersed. When you immerse it like this, some water will get displaced out. Some water gets displaced out. Now listen. When you immerse an object like this inside Lamai, there is an upward force acting. What is that upward force?
Upthrust.
It's a force.
Yes.
Some amount of water get displaced out. I keep a weighing scale there and measure the weight of the displaced fluid. I keep a weighing scale, measure the weight of the displaced fluid. Some water comes out, I can measure the weight there. 10 Newton, 20 Newton, 100 Newton, I can measure the weight. Weight of the displaced fluid, I'm going to measure. I measure the weight of the displaced fluid. Weight of the displaced fluid, not the object. Weight of the displaced fluid. Some water is coming out, that one's weight I'm measuring. Remember, the upthrust and weight of the displaced fluid are equal. They both are equal. Not magic. This is what Archimedes principle tells. That means, let's say you measure the weight here. If the weight here is 100 Newton, you all tell me what's the upthrust?
100
100
Newton.
Newton.
100 Newton.
100 Newton.
100 Newton. More important connection, eh? Because there is no any other way to measure the upthrust. Archimedes found the way to measure upthrust. Don't worry about the upthrust. Measure the weight of the displaced fluid. Some fluid is coming out. Surely when you partially or fully immerse object, surely some liquid will get displaced. You take it, put it in a container, measure the weight. That weight and upthrust are equal. Theoretically, practically, everythically, it's equal. If you want, you do it and see. You take an object, you put it inside, the upthrust and the weight of the displaced fluid will be. Now we'll put it into a nice sentence. What is Archimedes' principle telling us? When an object is partially or fully immersed in a fluid, maybe halfway, maybe fully, partially or fully immersed in a fluid, the upthrust acting is equal to the weight of the displaced fluid. That is Archimedes' principle. Again, what is Archimedes' principle? When an object is partially or fully immersed in a fluid, the upthrust acting is equal to the weight of the displaced fluid. Don't go to memorize the principle. Understand the logic. Using the logic, you all make sentence. What is the logic here? You put an object inside a fluid. Some fluid will get displaced. The weight of the displaced fluid and upthrust are what? Now put it into words. Object is partially or fully immersed in a fluid. The upthrust acting is equal to the weight of the displaced fluid. Where open the mouth and again tell me the Archimedes principle. Louder, open the mouth and tell. What is the Archimedes principle telling us?
The
When an
upthrust
object
and the
When an object
displaced
is fully
water's
or
volume is
partially
equal.
immersed
fully
in a
immersed in a fluid, the
Then
upthrust acting is
the
the
upthrust
upthrust
acting on
is
the
equal
object
to the weight of the displaced fluid.
equal to the weight of the displaced fluid.
weight of the displaced fluid. Perfect.
Excuse
When
me,
an
sir.
object is partially or fully immersed in a fluid, the upthrust acting is equal to the weight of the displaced fluid. That's it. That is Archimedes' principle. For example, now your turn. For example, you take your friend, put the fellow inside a container. Some water gets displaced. You measure the weight of the displaced fluid. Let's take the weight measuring there is 1000 Newton. 1000 kilo 100 you 1000 Newton. What's the upthrust?
1000.
1000 Newton.
1000 Newton.
1000 Newton.
1000 Newton. That's Archimedes' principle. Now for that only you all were wandering up and Archimedes' principle. When an object is fully or partially immersed in a fluid, then the upthrust acting on the object is exactly equal to the weight of the displaced fluid. Underline or highlight the principle. Huh? And that a box is given. Make an away. Cool, am I? I'll nicely draw. Draw. Write this box it. Yes, Ilham. Yes. So what is your real name? Honey, my real name is King Sperori.
Sir, excuse me.
Yeah.
A small doubt.
Yeah.
Doesn't that upthrust is equal to the real weight of the object?
No. We can't tell that. About that, I will teach separately. We can't tell that. It depends on the instance, Puta. I'll teach about that. Archimedes is telling only the relationship between upthrust and weight of displaced fluid. That's it. Real weight story, I will teach about it.
Okay, sir.
Okay. Done.
Yes.
Excuse me, sir.
Yeah.
I have a doubt on the applications of the atmospheric pressure in the daily life.
Okay. Go ahead.
Uh, Can't we use the siphon method when drinking the water with a straw?
Uh, Actually, they are also the same thing happens, but siphon method is specifically defined when you have to remove water from an object that is at a higher position to something to a tank or something at a higher position to lower position. That is how siphon method is described. A straw is not like that. No, you can't bend the straw. It's the direct application there.
Hmm. Okay, sir. Thank you.
Okay. Okay. Now that is Archimedes principle. Now, what is Archimedes principle telling? It is telling the relationship between thrust and weight of the displacement. That's the relationship. That's it. Archimedes coming. He is telling about upthrust, weight of the displacement. He is going. Only that part he is telling. Now, what's the relationship between upthrust and real weight of the object? Upthrust and displaced fluid weight, upthrust and weight of the displaced fluid, Archimedes is telling. Do we have a relationship between upthrust and real weight? Yes, we have. What is the relationship? That one we can formulate. Archimedes is not telling about that. He is telling about upthrust and weight of the displaced fluid. We are going to tell about upthrust and real weight. Upthrust and real weight connection we are going to build. What's the connection? We talk about the connection in 3 instances. Listen, will you? Object, partially immersed and floating. One condition. Object, fully immersed. Second condition. And sinking කියලා ගමුකෝ. And sinking. Object, resting at the bottom. First, I will draw diagram for all these 3 conditions. First condition, object partially immersed and floating. Object is partially immersed and floating. Object is floating, but slightly immersed. Correct? Object partially immersed and floating. Object fully immersed and sinking. Object is fully immersed. It is sinking. That means it's going down. Object resting at the bottom. Object has gone down. Now it is at the bottom. Again, read the heading with the diagram. Object partially immersed and floating. Halfway immersed, it's floating. Object fully immersed and sinking. Fully immersed, till it is sinking. Object resting at bottom. For each instance, you can talk about the relationship between upthrust and weight. For each instance, we are going to talk about the relationship between upthrust and weight. Upthrust and weight. What's the relationship? Right. Object partially immersed and floating. Now listen, now y'all are going to tell me. Object partially immersed and floating. partially immersed and floating. That means, is the object moving down? Y'all tell me.
No.
Is the object moving down?
No, sir.
No.
Is the object moving up?
No.
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 No, sir.
That means I can tell object is at equilibrium. Agree?
Yes.
Yes.
Yes, sir.
If the object is at equilibrium, what can you tell? Upward force and downward force should be?
Equal.
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 Upthrust and the weight should be?
Equal.
Equal.
So at this instance, upthrust and the weight are?
Equal.
Equilibrium.
Makes sense? No, it's not moving anywhere. It's at equilibrium. Equilibrium, upward force, downward force should be equal. Second condition. Object fully immersed and sinking. That means object is moving where?
Downwards.
If
Downwards.
the object is moving down, downward force should be?
Higher.
Upward force should be?
Low.
Less.
Low.
W should be greater
High.
than what?
U.
It's at the bottom. If it is at the bottom, still, which force is greater?
W.
Downward force
W.
is greater. W is greater than?
U.
U.
Now I know you all will be asking, so if W is greater than U, it should break the vessel and come out, no? Isn't it? Practically think. If downward force is greater, it can't be resting. How can it be resting? It should break and come down. But will it break and come down?
No. Sir.
No.
No,
Why?
sir. All right.
Why it's not breaking and coming down? Huh? Why the vessel is not getting broken? Now downward force is greater. Hurry. Perfect. One person answer. To balance the additional weight, there is an additional upward force. Guess and tell me. One person told it. Guess and tell me what's that additional upward force?
Upthrust. Upthrust.
Upthrust is already there. Additional upward force is there.
Atmospheric.
Now atmosphere is outside. Another person told. Third person told.
H2G.
A force.
Perpendicular.
Friction can rubbing against the surface.
Resistant force.
No resistance.
Newton.
Perpendicular force.
Gravitational force.
Perpendicular reaction. Onnapothe, two are in contact. Bottom and the surface are in contact. At a contact point, what is force upward?
Perpendicular.
Perpendicular reaction. So to balance the additional weight, you have the reaction force acting. Perpendicular reaction. Sorry, I'm not going to draw that, but keep in mind, their perpendicular reaction force will balance. Okay, these are simple things. Again, upthrust and weight of the object. When object is partially immersed and floating, upthrust equal weight. When object is fully immersed and sinking, weight greater than upthrust. When object is resting at bottom, weight is greater than upthrust, but specifically, there will be perpendicular reaction force there to balance it. That's it. One more additional point. What's the additional point? In this first instance, now this is the normal situation. Now what I'm going to do, I'm going to press this object inside. I myself exert a force and press it inside. For example, let's take regiform. I press the regiform inside. When I press the regiform inside, then what will happen? When I press the regiform inside, I'm exerting an external force. When I press it inside,
Upthrust.
and when I leave it, let's take, you press a regiform and leave it. What will happen to the regiform?
Come up.
Again, if you
Bounce
It
out.
come out.
from
Why it comes out? Why it comes up? What force is
Force of
greater when you press
upthrust.
it?
Upthrust is
Thrust is
the density of the regiform.
When pressed inside. when pressed inside. When you press it inside, upward force will become greater than the, you press the regiform inside, leave it, it will come up. Why? When you press it inside, upward force become greater than the weight. But you need to press it. Now, when it is outside, will the upward force be greater? If upward force
No.
is greater, regiform will fly. Regiform won't fly. When you press it inside, only upthrust will increase. Other than that, upthrust equal weight. So that additional part, keep in mind. That's the connection between upthrust and weight of the object. Is Archimedes telling this?
No.
No, sir.
We are telling. Archimedes is telling about connection between upthrust and weight of the displaced fluid. We have built, using our forces knowledge, equilibrium knowledge, we have built the connection between upthrust and weight of the object. W is the real weight of the object. There's a box given. Which box? Next page, there's a box. Special point. Relationship between upthrust and weight of the object. Big box is given. I want you all to write. Think and write. Nice, big connections. Is this theory used in rocket science? No. Rocket is fully based on Newton's third law. It's not based on this theory. That's Newton's third law. Every action has equal and opposite reaction. Upthrust is used only in water concepts, right? No, not only water concept, fluid concepts.
Finish, sir.
Okay. So what time you sleep? Is there something called sleep? Object partially immersed and floating, Newton's third law. Partially immersed and floating. Partially immersed and floating, no, Newton's third law. This is Newton's first law. Object at rest likes to remain at rest. That's why when you press it again, it comes to the normal position. Okay.
Done, sir.
Okay.
Done.
Quickly, we'll finish off the last part also. Last part. Hydrometer. What is this hydrometer? It's a device used to measure what? Used to measure the density of
Water.
liquids.
Liquids and solution.
Liquids and solutions. So it's a device used to measure the density of liquids and solutions. Any liquid type you can measure the density using a hydrometer. If you look at hydrometer, this part is actually called as the bulb. This part is the glass stem. Glass stem, you have the scale. In that scale, densities are marked. Inside the bulb, you have lead shot. And sir, why you have lead shot? Later I will explain. Now, how you measure the density? How you measure the density? How you measure the density? You take the hydrometer, put it inside the liquid. It will be floating vertically. Floating vertically can? Maybe it will be floating. If you look at the level of the hydrometer that touches the surface, that gives you the density of the liquid. If I draw it a bit bigger, this is the hydrometer. This is the liquid level. This is the scale. Let's take the scale is marked here as 1000 kilogram per cubic meter. Then what's the density of this liquid? 1000 kilogram per cubic meter. You put it at a certain level, it will be touching the surface. That level, you look at the scale. That scale gives you the density. That's how you measure the density using hydrometer. What's the principle? What's the working principle of hydrometer? Archimedes principle. It also works based on Archimedes principle. Okay. Hydrometer. Hydrometers are used to measure the density of liquids and solutions. It is made of glass. It has a cylindrical stem and a bulb as shown in this diagram. Mercury or lead shots are found inside the bulb to enable it to float vertically in the liquid. Now, I told you, what is there inside the bulb here? Usually lead shot. Sometimes even they put mercury. Why here they put lead shot? What's the reason?
To float vertically.
For
it
its
to float vertically. Why? When the bottom is heavy, it can float vertically.
Enable
Otherwise,
to float it.
if bottom is not heavy, when you put it in the liquid, it will slant like this. You take a pencil, put it in liquid, it will slant. You make the bottom slightly heavy and put it in the liquid now. It will float vertically. So make the bottom heavy for it to float vertically. The liquid or the solution is taken to a vessel and the hydrometer is put into it. Then the density of the liquid or solution can be read directly by the scale given. Hydrometer has been made in accordance with Archimedes principle. The hydrometer immerses in the liquid to a height so as to displace a weight equal to the weight of the hydrometer. The volume of the liquid or the solution displaced is equal to the volume of the immersed part of the hydrometer. Whatever the part that is inside and whatever the liquid that get displaced are equal. As a small volume of liquid is displaced in high dense liquid, the hydrometer is immersed to a small depth. This part I'll explain. I will give you all 3 solutions. Three solutions. Solution A, solution B, solution C. Solution A, hydrometer is there. Solution B, solution C. You all tell me which solution has the highest density.
C.
A.
C.
A.
C.
C.
Highest density. The question is highest density.
C.
A.
C,
A.
sir.
A,
A.
sir.
A.
C.
C.
C,
C.
Hari. Andai. Very good. Now I'll explain. Listen. Now, what is this density mean? Something like thickness of the liquid. Remember, when the density is high, thickness of the liquid also will be high. When the density is less, thickness of the liquid also will be. For example, let's take grease and petrol. Grease and petrol. Which one is thick, Lamai?
Grease.
Grease. That means density is high. Which one is thin?
Petrol.
Petrol.
Density is low.
petrol.
Now you take hydrometer. Keep hydrometer aside. You take pen. You put it in petrol. You put it in grease. In which one it will go to the deep?
Petrol.
Petrol, sir.
Petrol.
In which one it doesn't go to the deep?
Grease.
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 Why? When the density is high, thinking of the hydrometer is less. In high dense liquid, hydrometer thinks less. In low dense liquid, hydrometer thinks. Correct? No? You take grease, you put pencil or pen, it won't sink much. It's at the top. You take petrol, you take petrol, put a pen, it will sink more. When density is less, sinking is more. It goes to the bottom. When density is high, sinking is opposite connection. Now tell me then, ABC, which one density is high?
C.
C, sir.
C.
C,
C density is high. Why? Here sinking is less. If sinking is less, density is high. Opposite connection. If sinking is high, density is less. So if I write it and keep, density of A is less than, B is less than, C has the highest density. When density is high, thinking is less. When density is less, thinking is high. That is what is defined there. As a small volume of liquid is displaced in high dense liquid, the hydrometer immerses to only small depth. But when it is put in a low dense liquid, low density petrol, it is immersed to more because more liquid should be displaced to produce the upthrust required to balance it. Now box is given. Hydrometer sinks more in a less density and sinks less in a liquid of high density. In that box is given. Dingala, draw this and finish it off, Lama. Done.
Yes, sir.
Already started telling good night. This is the first time I have got your late night, ne? First time late night class for you. Come next day, will you know? Grade 10 is done. Come next day, I'll get you. Ta-da! Bye. Then, doubts, ask, please. So can you show the previous slide? This one, no? So can you send some third term paper? Now I guess y'all are in your holidays, near. Today holiday started, no? Some are having the exam. Hurry, hey, anything. Lesson is done, right? Some question. So why does water doesn't come out when we open one inflexible tube? Is it because of atmospheric pressure? When you open one input, there is no pressure difference. There should be a pressure difference, high pressure and low pressure. When you close one end, right? When you close one end and you keep the other end open, that doesn't cause a pressure difference for it to flow. හරි නේද? හරි නේද? Is this lesson important O level? අනේ අප්පා. Why did I do this lesson with this much of these things? Important නේ? හරි. හරි එහෙනම්. Not gonna waste any more time of y'all. Right, lesson is done. එහෙනම් our theory class students, I'll meet you all in the class. Others, I hope you all clarified whatever the doubts you all had. Okay. Okay, then this video will, however, all these 3 video will remain until you're dead. Until that time it will remain. So if you want any back again clarification, you can rewatch the video, especially this Archimedes principle part. Again watch it now because it's the first time you learned. Again rewatch it, put it to the mind. Okay. Okay then, enough for today. Keep working. I'll meet you all in the next class.
Bye, sir.
Thank you, sir. Bye, sir.
Thank you, sir.
Thank
God
you,
bless
sir.
you.
Thank you,
Okay,
sir.
God.
Thank you, sir.
Thank you,
Okay,
sir.
bye.
Bye, sir. Good night.